Derivation of the section formula. Welcome, everyone. Let's begin our lesson on the derivation of the section formula. Now, if you recall from our previous subsection, we explored how a point, let's call it P with coordinates x and y, can divide a line segment OB into two distinct parts, following a specific ratio, which we denote as m1 to m2. However, while we can visualize this on a graph, we run into a practical problem. If we want to find the exact, precise coordinates of point P without having to manually measure distances with a ruler on a coordinate plane, we need a more reliable algebraic tool. That is exactly why we need the section formula. In the upcoming slides, I am going to walk you through how we actually build this formula from scratch. You'll see that the entire derivation relies on a fundamental concept from geometry, the properties of similar triangles. So, let's move on to our geometric setup to see how this works. 1. The geometric setup. To make this more concrete, imagine a real-world scenario. Suppose you have two signal towers placed on a map at coordinates A, with x1, y1 and B, with x2, y2. A technician needs to place a receiver, which we will call point P, with coordinates x, y, somewhere on the straight path between these two towers. The requirement is that the distance from tower A to the receiver P and from the receiver P to tower B must follow a specific ratio, which we'll call m1 to m2. To find the exact coordinates of this point P, we can't just guess. We need to perform some specific geometric constructions on our coordinate plane. First, we draw a straight line segment joining point A, x1, y1, to point B, x2, y2. We then let point P, x, y, be the point that divides this segment OB internally in that ratio of m1 to m2. Next, to help us find the lengths we need, we drop perpendicular lines from points A, P, and B straight down to the x-axis. Then, we draw lines through points A and P that run parallel to the x-axis. Finally, we let these horizontal lines meet the vertical perpendiculars coming from P and B at two specific points, which we will label as Q and C. Now that we understand the goal is to find a formula for point P, let's look at how we set this up geometrically. By doing this, we are setting the stage to create the triangles we'll need for our proof in the next slide. Creating similar triangles. Now, if you take a look at the diagram we've just constructed, you'll see that by dropping those perpendicular lines and drawing the parallel lines through points A and P, we have effectively partitioned the space into two distinct right-angled triangles. Specifically, we are looking at triangle PAQ and triangle BPSI. Keep these two triangles in mind, because in the very next slide, we are going to use them to prove that these two triangles are actually similar to one another. 2. Applying the AA similarity criterion. If we examine triangle PAQ and triangle BPC, we can establish their relationship through their angles. First, by our initial construction, the angle AQP and the angle BCP are both 90 degrees, meaning they are both right angles. Next, because we drew the lines AQ and PC to be parallel to the x-axis, the angle PAQ and the angle PBC are corresponding angles, which makes them equal. Because we have identified that two angles in triangle PAQ are equal to two angles in triangle BPC, we can conclude that these two triangles are similar based on the angle or AA similarity criterion. We write this as triangle PAQ is similar to triangle BPC. Now, this similarity is the most crucial part of our derivation. Since the triangles are similar, the ratios of their corresponding sides must be equal. This gives us the proportion where the ratio of the hypotenuses, AP over PB, is equal to the ratio of the horizontal segments, AQ over PC, which is also equal to the ratio of the vertical segments, PQ over BC. We will use these specific ratios in the next step to substitute our coordinate differences and solve for our unknown point. Now that we have set up our geometric construction, let's look at how we can mathematically link these two triangles. 3. Substituting coordinate differences. We already know from our initial setup that the ratio of the hypotenuses, AP over PB, is equal to the given ratio, M1 over M2. To find our actual formula, we need to replace those geometric lengths with something we can calculate using coordinates. So, let's express the lengths of the horizontal and vertical sides in terms of our x and y values. First, let's look at the horizontal segments. The length of segment AQ is the difference between the x-coordinate of point P and the x-coordinate of point A, which we write as x minus x1. Similarly, the length of segment PC is the difference between the x-coordinate of point B and the x-coordinate of point P, which is x2 minus x. Next, let's look at the vertical segments. The height of our first triangle, segment PQ, is the difference between the y-coordinate of point P and the y-coordinate of point A, or y minus y1. Finally, the height of our second triangle, segment BC, is the difference between the y-coordinate of point B and the y-coordinate of point P, which is y2 minus y. Now that we have established that our two triangles, triangle PAQ and triangle BPC, are similar, we can move from geometry to algebra. By converting these lengths into coordinate differences, we are now perfectly set up to substitute them into our similarity ratio in the next step. 4. Algebraic derivation for $. Let's start by looking at the ratio of the horizontal sides. From our previous work, we know that the ratio of the segments, M1 over M2, is equal to the ratio of the horizontal lengths, which is x minus x1, all over x2 minus x. To find the formula for x, we need to isolate it, and the best way to start is through cross-multiplication. First, when we cross-multiply, m1 times the quantity x2 minus x equals m2 times the quantity x minus x1. Next, we distribute the terms. Multiplying this out, we get m1 x2 minus m1 x on the left side and m2 x minus m2 x1 on the right side. Now, our goal is to get all the terms containing x on one side of the equation. So, let's move the negative m2 x1 to the left by adding it, and move the negative m1x to the right by adding it. This gives us m1 x2 plus m2 x1 equals m2x plus m1x. Notice that on the right side, both terms now have an x. We can simplify this by factoring out the x, leaving us with m1 x2 plus m2 x1 equals x multiplied by the quantity m1 plus m2. Finally, to isolate x, we simply divide both sides by the quantity m1 plus m2. And there we have it. We have successfully derived the formula for the x-coordinate. X equals the quantity m1 x2 plus m2 x1, all divided by m1 plus m2. Now that we have established that our two triangles are similar, we can move from geometry into algebra to actually find the value of our unknown x-coordinate. This same algebraic process will be applied to the y-coordinate in our next slide. 5. Algebraic derivation for $. If you look at our construction from the previous slides, we can apply the same ratio to the vertical sides of our similar triangles. This gives us the ratio of m1 over m2 equals the quantity y minus y1, all over y2 minus y. To find the value of y, we will solve this equation using cross-multiplication, just as we did for the x-coordinate in the last slide. First, we multiply the numerator of the left side by the denominator of the right, and vice versa. This gives us m1 times the quantity y2 minus y, which equals m2 times the quantity y minus y1. Next, we expand the brackets by distributing the terms. This results in m1 y2 minus m1 y equals m2 y minus m2 y1. Our next goal is to group all the terms containing y on one side of the equation. To do this, we move the negative m2 y1 to the left and move the negative m1 y to the right. This leaves us with m1 y2 plus m2 y1 on the left and m2 y plus m1 y on the right. Now, we can see that y is a common factor on the right side, so we factor it out. This simplifies the right side to y times the quantity m1 plus m2. Finally, to isolate y, we divide both sides by the quantity m1 plus m2. This leaves us with our final formula for the y-coordinate, y equals the quantity m1y2 plus m2y1, all divided by m1 plus m2. Now that we have successfully derived the formula for the x-coordinate, we will follow the exact same logic to find the y-coordinate. As you can see, the structure of the formula for y is identical to the one we found for x. Key takeaways. To summarize our derivation, the most important thing to remember is that the section formula isn't just a random rule. It is fundamentally derived using the concept of similar triangles. Specifically, triangle PAQ is similar to triangle BPC. As we saw in our step-by-step proof, it was the AA, or angle-angle, similarity criterion that acted as our bridge. This criterion ensures that the ratio of the hypotenuses is exactly equal to the ratio of the horizontal legs and the ratio of the vertical legs. This relationship is what allowed us to set up those algebraic equations in the previous slides. So after all that algebraic manipulation and solving for our unknowns, we arrive at our final powerful result. The coordinates for our point P, which we call x and y, are given by these two formulas. First, x equals the quantity m1 times x2 plus m2 times x1, all divided by the quantity m1 plus m2. And second, y equals the quantity m1 times y2 plus m2 times y1, all divided by the quantity m1 plus m2. All right, let's take a moment to recap everything we have just worked through. Now that we have the formula itself, let's look at some common pitfalls to avoid when you start applying this to actual problems. Common mistakes. First, watch out for swapping your coordinates. This is perhaps the most frequent mistake I see. When you are using the formula, remember that the ratio part m1, which is associated with point A, must be multiplied by the coordinate of the opposite point, which is x2 from point B. Conversely, m2 must be multiplied by x1. A good way to remember this is that the parts of the ratio cross over to the opposite ends. Second, be extremely careful with sign errors. When you are dealing with coordinates that are negative, it is very easy to lose track of a minus sign during the addition or multiplication process. To prevent this, I highly recommend always using parentheses when substituting values. For example, instead of writing it loosely, write it as m1 times negative x2 plus m2 times x1. This keeps your work organized and clear. Finally, make sure you are interpreting the ratio correctly. Sometimes, a problem won't give you a ratio in the form of m1 to m2. Instead, it might be given as k to 1. In such a case, you must identify that m1 is equal to k and m2 is simply 1. Now, before we wrap up today's lesson, I want to touch on some common pitfalls. Even when you understand the derivation we just walked through, it is very easy to make small errors during calculation. If you keep these three things in mind, you will find that applying the section formula becomes much more reliable and accurate.